Okay. Hi, everyone. Welcome to Compass every Wednesday and Friday, so nothing too new. Today, I'm very excited to introduce Dr. Rachel Gaal for our Wednesday Compass talk this week. She received her bachelor's in science and meteorology with a minor in mathematics from the University of Oklahoma in 2016. Between her undergrad studies and graduate studies, she worked as a staff science writer for the American Physical Society and a communications coordinator for the NOAA Climate Program Office. So if you need help writing, go to her. Dr. Gaal recently finished her PhD this summer at George Mason University, and the title of her dissertation was The Role of Soil Moisture on the Incidence of Summer Mesoscale Convective Systems in the U.S. Great Plains. Now, she works as a postdoctoral researcher at the University of Miami, working with Ben Kurtman on creating a hyperlocal climate projection. Outside of the 40-hour commitment to Erasmus, Dr. Gaal can usually be found in the great outdoors. She's an avid backpacker, hiker, and runner. Dr. Gaal is also a foodie, so if you have any food recommendations for Miami, make sure to let her know after the talk. And with that, I'd like to introduce Dr. Rachel Gaal.
Thanks, guys. Thank you for coming today. I didn't realize that the climate series was today, so I picked this day unknowingly, but that's okay. Thanks for coming anyway. And if you need to leave during the talk, that's fine as well. So today I just want to talk to you guys about my dissertation work. I wish I had something to talk about with my new project, but that's just getting started. So I figured I'd talk about what I've been doing for the past 5 years, since there's plenty to talk about. But to give some motivations about what got me interested in this topic in the first place, I went to school at University of Oklahoma for my undergrad. I was really interested in mesoscale convective systems and how they always flood in Norman, Oklahoma. So those events got me interested in the science of mesoscale convective systems. And I wanted to figure out how I could increase the predictability of these storms in the summertime. And the main thing that I wanted to know about when I first got into graduate school was what the role of the larger scale atmospheric environment was for these particular storms. And I started grad school in 2018, and these particular papers that are on the screen, they came out in 2019, so just right after I started. And they did a really good job at actually explaining the spatiotemporal characteristics of these storms. And with that said, I didn't think that I really could contribute more to their studies, since they did such a really good job at understanding the large scale environments where they thrive. And they also did a really good job at explaining future avenues of work, such as the fact that they alluded to influences of the land surface as a possible driver of these initiations under weakly force conditions in the summertime. So at first, I didn't really think much about that comment, but then I took a land atmosphere interactions class and realized how important the land surface is in actually relating to precipitation onset. And so with that, I wanted to see how I could relate soil moisture precipitation coupling to mesoscale convective systems. And this is just a general outline of how soil moisture modulations can create or suppress precipitation. And it really starts with the near surface variables, such as 2-meter temperature and 2-meter humidity, being affected by the surface sensible and latent heat fluxes. And those are the defining characteristics of the boundary layer. And ultimately, that's going to suppress or allow for the formation of clouds and precipitation. And I put an asterisk on the precipitation and clouds term, mainly because this feedback is mainly associated with, I would say, pop-up convection, things that are unorganized, unlike the mesoscale convective system, which is a highly organized type of event. And usually this type of feedback is not associated with the mesoscale convective system. But that doesn't mean that people haven't looked at that before. These are two particular, I guess, geographic regions that I have found papers on that have looked at this particular relationship. And in the Great Plains, it's more so of a positive feedback where you have mesoscale convective system events wetting the soil, and then future MCS events occur over those particular areas. But in the Sahel, where MCSs currently or often occur, it's more of a negative feedback. So they're occurring more over drier soils in that area. And they also found, the authors of those papers found that soil moisture heterogeneity can influence the location of these initiations if aligned in a certain way with the mean background wind. So that's particularly important considering, there are two conflicting results, but also the fact that these particular studies, they look at, characterizing the soil moisture, but they're not necessarily identifying a mechanism of interaction between the soil moisture state and the MCS initiations. Another thing that those studies don't necessarily do is identify or, subset between strong and weakly forced synoptic environments, which I think is a pretty important component of identifying a land-atmospheric feedback, in relation to MCS events. So with this information gap, when I started the program, I came up with 2 or 3 main research questions, got whittled down to 2 so I could graduate on time, but mainly the fact that we want to be able to characterize favorable soil moisture conditions in the Great Plains in the summertime for weakly forced synoptic events of MCSs to basically look at what the soil moisture looks like in that particular time frame, I would say. But then also going a step further and identifying a mechanism of interaction between those two things to better understand what is going on rather than just a characterization. So the rest of this talk is just going to be split up into 2 parts. The first part, I'm just going to go over more of an observational analysis where I'm looking at the favorable soil moisture conditions, and I'm hypothesizing based off of previous literature, actually in the Sahel rather than in the Great Plains, mainly because the Great Plains study was a case study and not necessarily looking at a larger subset, which the Sahel Desert did. So thinking that heterogeneous conditions are going to be important in the initiation of these storms was my hypothesis to begin with. But in order to look at something other than a case study, you need, a large sample of MCS cases. And basically, when I first started the program, I don't know how this happened. I think it was a gift from God, but somebody published a repository of MCS events from 2004 to 2017 east of the Rocky Mountains. And that was a gold mine in terms of data. I mean, it was thousands of cases that I could use to study, and they did a great job at characterizing all of the different attributes of these storms. So I went ahead and used that particular data set, and I subsetted using a selection algorithm to basically look at boreal summer events during the daytime in the Great Plains, but also looking below a certain elevation to remove the possible effects of orographic lifting at aiding the initiations. And then I also wanted to exclude squall line events. And the main reason for that is due to the fact that a passing frontal boundary would be considered a strong synoptic forcing for those particular storms. So I wanted to exclude all the storms that had that type of characteristic. And in the data set, they actually did characterize by that using eccentricity data or values to just characterize if it looked like a squall line or not. So I did that. And then I also verified using a CTP high-low analysis. That's basically a fancy way of saying we did a land atmosphere metric to look at how morning time soil was affecting the moistening and deepening of the boundary layer. So basically, I just wanted to verify that the characteristic that I was choosing in this data set did a good job of actually choosing the data or the data points that I cared about, which is events that are most likely to be influenced by the land surface. So I went ahead and chose about 240 cases based off of that selection algorithm. And then I wanted to look at the soil moisture and 2-meter temperature data for those particular events. And I wanted to look at the antecedent time for these particular storms, mainly because morning time conditions have been shown in literature to be most important in influencing afternoon convection, even though it's not linked to mesoscale convective systems per se. But using that information, I thought it was important to look at antecedent and then also to remove the possibility that rainfall is happening at initiation. So the soil moisture would be affected at that rate. So looking in the morning time hours, I'm basically doing a storm-centered composite analysis where I'm centering a giant, basically a 5x5 square domain, and I'm just picking out the soil moisture and the 2-meter temperature from that particular, from that case, and doing it 240 times for each case. Then I'm aligning and averaging all the LB domains to create a mean composite figure to look at what is the mean soil moisture and 2-meter temperature antecedent to initiation. So this is the result of that particular analysis. There are 2 plots because one of them, figure A, is the anomaly field, and the figure B is a full field of soil moisture and 2-meter temperature. So all the colors are basically soil moisture, and the black contours are 2-meter temperature. So you can see in figure A, you have drier soil moisture transitioning from the southwest into moister soil moisture in the northeastern regions. And this is at the 5 by 5 degree scale. So this is pretty substantial in terms of soil moisture heterogeneity being present at that large scale. You can see if you center in on the very middle of where the initiations are happening, that it's occurring over anomalously drier soils in the smaller scale. But by zooming out, we were able to detect this large scale heterogeneity that was present in the vicinity of these initiations, and significantly as well, at the 95% level. So the full field on the right-hand side is shown mainly to just address the fact that the atmosphere is responding to the absolute values of soil moisture and temperature, not necessarily focusing on the anomalies. So the fact that these patterns are reinforcing one another, so the full field is the same type of orientation as the anomaly field, means that this is a pretty substantial type of pattern that can be reinforced by the background field. And that is also significant as well. So this is a great characterization, but we also wanted to look at how it's aligned with the mean low-level wind field. And in this case, we can see that there is southwesterly flow, which happens to be parallel to the gradient direction in this case. And so this is combined with the convergence of wind, both through veering with height, which isn't shown, but the winds do veer with height. And they also have a decrease of wind magnitude over the transitional and wetter portions of the domain. So this convergence over the transitional areas of soil moisture is kind of giving parcels a boost in terms of being able to converge and go upward in order to initiate these storms. And I kind of jumped ahead and said what my schematic was that we came up with for this paper. Basically, that we believe that the soil moisture and temperature gradient aligned with the background wind is what's responsible for initiating these storms at that particular time. But I think an important thing to note, and where we left off for this analysis, was that, you know, it was something that was a hypothetical mechanism. We didn't necessarily prove this in our paper, and I think that honestly goes beyond the scope of this paper as well. And you need to do a sensitivity study for that. But this was a good primer for us to be able to understand if this process can serve as an important influence in the dynamic and thermodynamic processes in the atmosphere. So taking this information and the composite that I made that showed the large scale heterogeneity, I wanted to basically use that in another hypothesis for a modeling analysis. So basically looking at what the mechanism of interaction was between soil moisture state and MCS initiations in these same weak large scale environments, but hypothesizing that that gradient is important and necessary for those particular initiations to occur. So using the same analysis, or the same cases, I basically wanted to test the hypothesis with a numerical model. And to test this mechanistically, we kind of just want to put a perturbation into the model and see what the model does. It's a pretty simple like flow chart that I kind of made in the left-hand corner. But basically, we're looking at if we can get an MCS event to happen with a perturbation similar to what we found in the previous study. But you know, obviously it's much more complicated than that. You know, there's lots of different ways that you can put in a perturbation, you know, what size you put the perturbation, how long does the perturbation persist for. There's lots of different things you could do, but we decided what we should do for this particular analysis was try 5 different experiments with varying orientations of gradients And also just single state, like this, for example, is circled because I'm going to talk about this experiment in particular, but just having, completely dry in a perturbation or completely wet, or having an orientation of a gradient in a certain way so it's aligned with the background wind. So we tried all these things to see if we could manipulate where the mesoscale convective systems occurred. And for this presentation, because I could talk about all of them, but the one that was most interesting to us was the circled one, which is perturbation 1. So I think it might be covered up by me in the corner, but it's supposed to say that these perturbations are basically the same scale that we looked at in the previous analysis. So it's 5 by 5 degree scale. And we basically center it on the initiation of an MCS recorded in MCS 2019, that data set. So using the same data set, we're basically taking observational data and looking at where these storms were recorded to happen, and we put a perturbation there in the soil moisture. Then we start the runs at 12 UTC and integrate through 24 hours with hourly output. To give you an example of what this looks like, because it's kind of crazy how big the 5 by 5 degree scale is if you put a perturbation in there that, for example, PB1, you take, this was our methodology at least, we took the control domain values and subtracted 2 sigma to make it significantly drier than the rest of the domain. But you can see it's kind of boxed in the red over on the right-hand side that we inherently get an area of drier to wetter transition between soil moistures. And we actually first decided to blur it out, so that didn't happen. But we thought, okay, if we actually implement this artifact of just placing an actual perturbation in here, we can maybe manipulate where the mesoscale convective systems happen. So we wanted to see if that was the case, and figuring out if we could get mesoscale convective systems to initiate near the boundary of those transitional zones. But we should probably talk about the model first before I get to the results. But basically, I was using the weather research and forecasting model. It's a highly customizable experimental model that you can use for any type of atmospheric experiment, really. But this is the domain configuration on the right-hand side. So the previous figure I was showing you was basically that whole inner domain, which is DO2. And then it's actually a two-way nested simulation, meaning that all of the data from the coarser domain to the finer resolution domain, they communicate for each time step. And all the static and meteorological data for the nest, they're obtained from the nest input file rather than being interpolated from the coarse grid, which is what makes a two-way nested grid kind of special rather than a one-way nested grid. And then just making sure that all the parameterizations we're choosing are able to simulate MCSs. That was probably one of the hardest parts of the experiment, is just figuring out which knobs to turn at what time, and making those configurations work for our experiment purpose. And I can give more details about that at a later time after the presentation if you're interested. But mainly the point to note is that we had 97 total cases that occurred within this DO2 that we decided to use as our sample size for these particular experiments. So I'm just going to go back to this. So basically 97 cases means 97 runs for control. Then you have to do that for every single experiment. So we're on the order of 400 to 500 runs of WRF. I mean, it was it was a lot, but at the same time, these runs were only 24 hours in length, so it didn't take that much computationally, but it still was, tedious to do. So keeping that in mind, how do you organize all that data? And basically what we decided to do was track all of the experiments and look if an MCS happened or not. And we used a specific tracking algorithm to do so, which is based off of brightness temperature and basically a size threshold for these particular storms to occur. And then we're basically doing a storm-centered composite analysis again, but at this point we're looking at soil moisture, and what we want to look at is is there a configuration that suggests that the MCSs have moved relative to control? So we're going to look at those now. And I wish the screen wasn't yellow, but anyway, so these are the average total soil moisture fields centered at each initiation in space and time. So it's basically representing what the average soil moisture looks like at that 5 by 5 degree scale. And you can see basically that the control doesn't show any pattern per se in terms of spatially organized soil moisture. But in PB1, you can see that there's organized soil moisture heterogeneity present, which to us, when we saw this figure, suggested that, okay, the locations of these MCSs are moving. Is it related to the perturbation that we implemented into the model? So yeah, I actually think that's at a later slide. But the point being is that this is a great characterization to have, but we want to go back to the main point of this total experiment, which was to find a mechanism of interaction for these specific storms to basically say, okay, the soil moisture is affecting the actual thing. Yeah, Amy?
I don't understand too. You meant to put in a homogeneous area of reduced soil moisture.
Mm-hmm.
And this is what the model put out. I mean, this was what the model simulated in terms of the soil moisture changes under the...
So basically, yeah, this is so when we ran the model, it ran for 24 hours, right? And then we took a tracking algorithm to basically say, okay, where did an MCS occur? So we're basically taking the points of where the MCS occurred and looking at a box around it to say, okay, what is the soil moisture around it? So that can be at a different place of where we put the perturbation. So if that makes sense, I'll give you a hint. Basically, the soil moisture perturbation, the MCSs are occurring around the boundaries of that, but I'll get to that at a later slide. But the point being is that, this is the clue of like, okay, they're obviously not occurring in the same place as control. I actually can skip all the way to that. I'll come back to this stuff, but point being is that this is the hypothesis that we had, basically saying that, if we have a mean wind orientation in the Great Plains and it's occurring over this transitional zone, we have a preferred area of initiation basically in this red area. And so that previous figure suggested that we actually see a movement of these particular storms around these boundaries. And it happens to be the fact that, if we plot those specific storms with, for example, in this case, the southwesterly flow, we see that the storms are happening around or within that preferred area of initiation relative to the implemented soil moisture pattern. So the transitional zone is what's important in terms of this particular analysis, where everything is occurring on the drier side. So basically this whole inner area is where the soil moisture perturbation would be. So the storms are occurring on the drier side relative to the transitional zone, which would be around the borders of the perturbation. So, okay, I gave away the secret, but let's go back and just look at, what the mechanism is in terms of this particular process. And we can look at it through this particular lens. I mean, it's not like I have to come up with a completely new framework to look at, but can we confirm that this is what's happening in terms of the relationship to, the soil moisture gradient influencing precipitation, and in this case for mesoscale convective systems? So the first leg of this chain is basically looking at soil moisture and evaporative fraction. And so we can see that the actual pattern of evaporative fraction for the same type of analysis, it shows that, you have more sensible heat flux over drier areas of soil moisture, and vice versa for the moister areas, which have a higher latent heat flux, so a larger evaporative fraction. And so these patterns suggest that these two variables are highly correlated. And if we look at this bottom chain, we can basically conclude that the evaporative fraction in this case, will be highly correlated with the 2-meter temperature and 2-meter humidity. At least that's what we can assume. So we looked at that. There's another analysis that I realized I didn't put in here that suggests that those two variables are correlated, but this is another one that shows that the evaporative fraction is highly correlated with the near surface variables such as temperature and humidity. Now, on average, it's, not, a perfect one, but at the same time, comparatively to control, we're seeing the needle move in terms of the relationship to these variables relative to the lack of relationship in control. Excuse me. Okay, so this is another plot that takes a second to explain, but I think it's really relevant because I think it tells a really good story. But basically the pink plot that you see at the top, it's a zonally average storm-centered composite. So if we take the composites that we looked at earlier for temperature and humidity, and we zonally average them and plot it through time, we're basically removing the x-axis and then plotting through time on the x-axis, and then degrees relative to initiation latitude is the y-axis here. So we're basically looking at 2-meter humidity shaded as a color, and then 2-meter temperature contoured as the black contours. And rather than looking at a full field, I'm taking that particular variable and subtracting the control variable. So basically all the pink colors mean it's drier than the actual control run, and conversely, a green color would mean it's more humidity relative to control. So in this case, we can see that there's a clear gradient of 2-meter temperature and 2-meter humidity that increases throughout the day, which could be associated with diurnal heating. But we looked at it relative to control, and it looks like it's being influenced by the actual soil moisture. But the reason I have it paired with this plot is because if we look at the LCL deficit, which is basically looking at the difference of height between the PBL height and the LCL height, we want it to reach 0 in order for the deep convection to be triggered. So we're seeing that the maximization of this gradient is occurring around the same time as the LCL or the PBL is crossing the LCL. So we're getting closer to figuring out whether or not these variables are related, and if the near surface variables are driving the growth of the planetary boundary layer. So that, I think, is important for the thermodynamic portion of this. But, is the dynamic portion of the analysis, helping or hindering the initiation of these storms? And we can see that in this particular, and it's kind of covered up, but this is the 900 millibar wind field at 1 hour before initiation. And we're looking at that because of the fact that we don't want the mesoscale circulations associated with the storms to be interfering with the background wind, basically. So we're looking an hour beforehand. And we can see that we have a south-southwesterly flow in the southern portions of the domain, but we also have cyclonic rotation, which is indicative of warm air advection, dynamical lifting. And then we also see something similar to what we had in the previous analysis, which was a decrease of magnitude of wind fields over the transitional and the northern portions of the domain. So all of this is indicating that there's convergence going on in the domain, and we can see that with the red colors of the shading in the plot, which is also indicative of convergence. So with that said, we figured that, okay, if this is all connected and driving the PBL towards the LCL, is it happening at a different time than control? Because we can obviously pin down a mechanism, but it's more so helpful to figure out if there's a time difference. And we found out by looking at the tracking algorithm that the storms in the PB1 experiment are occurring 1 to 2 hours beforehand of comparatively to the control. And we can also see on this plot on the left-hand side that the storms are not only firing earlier, but they're growing towards a larger area. So this is the threshold you need to meet in order to be considered an MCS, basically. So that obviously happens for both of these storms because we're tracking these events, but one happens earlier in time. So PB1 happens earlier in time, but it also occurs such that the area of these particular storms is larger comparatively to control, on average at least. So with that said, that's the main part of the analysis. But in terms of pinning down a mechanism, we came up with this idea in the initial analysis. But, we were able to kind of better understand, how this soil moisture gradient is related to this particular setup, where if you have a gradient of sensible heat flux, it can drive the planetary boundary layer upward over the drier portions of the domain, which is associated with like a negative feedback. And so the PBL in this case is meeting the LCL earlier than control, which was something that we found to be an interesting find. And then, I already went over this, but we basically wanted to confirm that the gradient of soil moisture was important in initiating these storms. So again, to go back to this particular plot, the initiations are basically occurring over areas that are drier relative to the surroundings, but they are occurring within the vicinity of the transitional zone of soil moisture, such that you basically need to, I thought there was another slide. You basically need to have this particular setup in order for these to occur. So the impacts and significance of my work, it's definitely not perfect, but it was a first for a few of the things listed here. Namely, I hadn't seen anybody use WRF for this purpose in terms of implementing soil moisture perturbations into the model. And then characterizing the soil moisture conditions for such a large sample was also a unique finding, or a unique product, I guess, that came out of this dissertation. But the main thing that I got from doing this work was knowing that the background wind could represent, or having the background wind oriented with local soil moisture anomalies, such that the dry soil moisture is upstream and the wet soil moisture is downstream of these particular wind fields. That could be a source of predictability for locating these particular events in the Great Plains. And I think that is it for the slides that I have. So yeah, I'll take questions.
Introduction. So we have about 20 minutes for questions, if anyone has any.
Yeah, I was curious about the convergence that you're showing. Is the convergence being driven by boundary condition, or what's driving the convergence? I guess is my question. Or is it just an artifact of the development of the MCS that you're getting right in the motion to get there?
Right. So we tried to investigate this question a little bit more by looking at like surface meso-β circulations as maybe driving the convergence as well. And it's hard to do that with such a large sample. Like if you looked at one case, it could maybe be easier to do like a vertical profile of what's going on, right? But with such a large sample, we weren't necessarily able to do that. But it really was just the fact that, if I go back to that, the wind field in this case was what was important, because we kept seeing this cyclonic rotation within the area. And even if you look at times before, an hour before initiation, this was the setup. So we think that the wind field aligned with the soil moisture is basically driving that convergence.
So the convergence precedes the initiation.
Yeah. Mm-hmm. Mm-hmm.
What does this mean for prediction systems? Are they how would they change the result? How would you want prediction systems to change or not change?
That's a good question. I think that the the main thing that I got from this study was just the fact that if you have areas of drought and areas of not drought at a large enough scale, you should be able to use that as a precursor to say, okay, if you have the right alignment of wind field, you could get a mesoscale convective system, or at least a severe outbreak within the vicinity of that area. Whereas usually it's, more synoptically driven. So I would it's not that I have an expectation of like things changing based off of that, but I think that having that information is, something new.
Might be more confident prediction. It just like looks like a statistical prediction, but you're saying actually it makes sense because of this setup.
Yes, absolutely. Yeah. Mm-hmm.
Yeah. The thermodynamic vertical structure that come off the boundary there, that's all staying the same.
The thermodynamic structure of of above the boundary layer.
Structure above 900.
Yeah, I don't have it in this particular presentation, but we did do like sounding profiles of what everything looked like. And we were able to determine that above the boundary layer, things are pretty much staying the same. Yeah.
I like your PBL minus LCL thing. I hadn't seen that before. Is it because the PBL, so you have a drier land, you'll get a deepening of the PBL?
Basically.
Wetter land, you'll get a lowering of the LCL.
Right, exactly.
So which one is changing? Which one's driving that difference?
Right.
It's the PBL going up. Maybe what you've shown it.
Right.
And in a wet case, the PB minus 2, plus 2 or whatever, you might have the LCL come down, right?
Right. So we looked, I didn't show the results of the other experiments, but we found something similar to that basically. So I had a perturbation that was like all wet instead of all dry, and we basically saw what you were saying for that.
That can still happen.
Yeah.
This curve might look the same, but in that case, it's the LCL coming down.
Yeah. We found that the timing though for these particular storms was happening such that the PB1 experiment was happening before all the other ones. And I think that's because you're driving the boundary layer height, higher, faster with that heat expansion of the air. So yeah, so that's what we found, but definitely a good point that it can be a different mechanism.
And do you know if it's really the gradient downwind? You don't know, is it just 2 degrees downwind of a dry patch? Or is it on the gradient between a dry patch and the not quite dry patch?
Yeah, it is definitely hard to tell. I think it would have helped if we had a smaller amount of cases to really look at those and say, and really pinpoint where they were occurring. But with such a large sample, 100 cases, it really depends. So yeah.
Lovely piece of work, yeah.
Thank you.
A lot of babysitting of the model, actually.
Yes, I think that was most of my time of my dissertation, yeah. Ida?
So
Yeah.
it does get like an oscillation if it rains, it moistens the soil, and it dries out. Sand. How long does it take? I don't have a good feeling for how many days without rain being able to get here, like -2
Right. Honestly, I think it obviously varies on the type of soil that you have, but in the Great Plains, it would take about like 3, 4, 5 days to not get significantly drier, but to remove that anomaly basically. So, it also depends on the temperature of the air in terms of, how hot it is and how fast that moisture is being removed, and also how dry it was beforehand. So a lot of factors go into that. Yeah.
You looked at
2004 to 2017.
So during those years, there was a few El or La Nina events, right? Do you think there's some impact for getting to that?
Yeah, that's a great question. I don't actually know. I think that since I've been here, everyone has been so focused on teleconnections, and it's crazy because I've been so focused on just soil moisture for so long that I forgot the big picture kind of. But I'm sure that there's a relationship in some way. Yeah. Yeah.
For one last question. One of your motivating slides, I thought it showed that you're more likely to get these more human.
Yes, that was one of the study. It is one study that I picked out that I thought was important, but in terms of that type of feedback, that was a positive feedback, right? Because more moisture includes more precipitation. And even so, nocturnal MCSs really thrive off of the low level jet that comes through. So you would think that in the Great Plains, especially, it would be more of a positive feedback. But this isn't to say necessarily that they're wrong. They just looked at one or two cases. So trying to characterize more than a handful of cases this is what we got for the results. But there's something else I was going to say with that. The fact that it's really the gradient, not necessarily just it being dry, I think is more so indicative of there being a relationship there rather than it just being a feedback. Because in the other, if I go to these particular papers, so the ones on the right hand side are really saying that they think the low level wind field being aligned with the dry gradients or the dry soil moisture is what's driving meso-β circulations at the surface that are helping initiate these storms. So that's, I see what you're saying though, in terms of it being conflicting.
Yeah, I'm just wondering how to reconcile the two. But I think what you're saying is that the paper on the left there was looking at a smaller size.
Yeah, they actually didn't really account for the synoptic forcing at all. They just chose basically a case set where they had multiple storms over multiple days, so kind of building off of one another. So that's what the corridor events means, that they're happening in the same corridor type of thing.
Last call for questions if anyone has any more. Well, thank you again, Rachel. This was such a good presentation.
Thank you. Thanks, guys, for coming.